Hi, Peter.
Well,
Okay, so no attendees yet, but and that's Shannon in as well. And then for the Q&A, I think we finally figured it out at the end of Twist last year. So I can ask the questions if you want, or if you can see them.
I think it might be best to have you ask the question so that way everyone can hear.
Oh, right. That's what we found out last time. Yeah.
What the question is.
That's right. We realized that last time. I got to go lock my dog up. I'll be right back. Come on, biscuit. Yeah, we got a nice bump of people there at the end, Peter.
Yeah, I looked over. It looks like most of the resellers. It looks. I mean, a lot of the emails I recognize as customers of other products too.
I know, like Allie from Halliburton and stuff. So
Yeah, which also so Robin said last night that he was going to buy
yeah,
VSIM
yeah,
and is looking at RSim too. So
yeah.
that's the hope of this whole thing, right? Is the double sale.
Yep. No, that's awesome. That's awesome. So, and I've got it's live streaming on YouTube now, and recording on my computer. So I think we're good. Okay. You can see it on the Zoom. I'm just making sure YouTube updates for us. Good morning for those of you who have just joined us. We'll get started here in just a few minutes. And welcome. Hello and welcome to those that have just joined us. We are going to wait. We'll probably start at about 10:03 because we know we have a few more guests that are coming in. But thank you for joining us today. Is that good with you, Peter? Let's do 10:03.
Yeah, always start 3 minutes late for a Zoom webinar.
Right, exactly.
That is the average login time if you are logged out of Zoom.
Right.
Based on our internal meeting experience.
Exactly. All right, we'll start in about 1 more minute. All right, well, it looks like we should go ahead and get started. Hi, everybody. Welcome to our introduction to RSim. I guess it should have probably said 3.0, right? I just realized as I look at it. Thank you, everyone, for joining us today. In this webinar, we're actually very fortunate to have one of the lead developers on this product, Peter Nielsen. He's an application engineer for TechX as well. And he's going to be discussing RSim, talking about its capabilities, doing a bit of live demonstration, and then of course, talking about some of the new features that have come out in this latest release that we're very excited to share with you all today. So having said that, Peter, I think it's your turn.
Yep. And so thanks for that introduction. I've been an applications engineer with TechX for almost 8 years now. And in the past couple of years, I've been working a lot in the development of this RSim product. So if you're unfamiliar with TechX as a company, it was founded in 1994 by two computational physicists, Dr. Carey and Shasharina, dedicated to computational physics research and software development. And many of you might be familiar with our flagship product, VSim. This is a finite difference time domain code used for particle and cell simulations. USim is a high density plasma CFD code, and RSim is our newest product based on doing radiation transport via Monte-Carlo simulation. So RSim was a product that we developed in collaboration with NASA with a particular focus on ease of use and work with complex geometries, especially things like if you have a CAD file, for example, this particular CAD file I know has about 500 individual parts to it. And we are able to import it in RSim and do a analysis of the radiation on this entire part without any difficulty, no time setting it up, just hit import and run. And so in our work with NASA, we've found that this is a useful tool if you're doing satellites or sensitive instrument protection, particularly things like shielding thickness optimization and analysis. It also does have use in accelerator physics, looking at the design of a detector as well as for radiation safety, and similarly for nuclear reactors, doing shielding designs. The one we found most important for satellites in particular is this thickness optimization. Every pound that you can save off the thickness of your shielding reduces cost. And so RSim has somewhat unique to the space of doing a commercial Monte-Carlo transport simulation code, a full GUI driven workflow with integration with CAD and GDML. So we can import CAD files and actually perform operations on them, editing, and one of the most important being shape healing. We can fix up a CAD file automatically and then export it into GDML automatically for use with RSim, as well as for other radiation transport codes often make use of the GDML format. Now, all of those CAD parts themselves can also have a material assigned to them, of which we have over 700 built-in materials and the ability to create any complex material, any alloy that you would like by combining those. We have a wide variety of particle sources. Typically, most commonly you'd see used for something like this is a spherical particle source, but we can also do point and planar sources as well. And we can have tallies, also depending on your experience with Monte-Carlo transport, sometimes referred to as scores of many different varieties. And we can actually apply that scoring to a shape of the simulation, say this foot, a mesh, if we were to place a mesh over this entire body, or a probe, which is a computational construct that doesn't exist in the actual simulation anywhere in the simulation space. We also have an automatic visualization of all of these and are developing optimization techniques. So there are some things that RSim does not have. We do not have input decks. We do not have input cards. There is no need to write C++ code. It is just like our vSim product, entirely GUI driven, point and click, and set up your simulation and run, allowing you to not have to focus on some of the computational aspects or some of the build things, like actually having to compile your code to run a simulation. Now, we do this with our validated physics, incorporating the GEONT4 code. If you're unfamiliar, GEONT4 is a European project. This is one where typically if you wanted to write a simulation, you would actually have to write C++ code. And we do away with that. And so we normally do electromagnetic physics from the electron volt level to the petavolt level. We have weak interactions, hadronic physics. There are some similar codes you may be familiar with for which RSim can oftentimes replace them, such as MCNP, FITS, Feluca, and Novice are all sort of in this similar group. So getting into the actual setup of the simulation, you'll see here, this is a snapshot of what our setup window would look like. If you're familiar with our vSim product, and I'll actually just bring up a generic full view right here. If you're familiar with our vSim product, this will look very similar to you, although the contents of some of these things have changed, obviously. But you can define your constants and parameters, set up the basic settings of your simulations, pick your physics. And what we'll look at right now is the geometry specification. Now, you can create an entire simulation out of geometry primitives. We call them constructive solid geometry. So things like spheres, boxes, a torus, anything like that, we can actually create and combine in real time so that you can see here. I'll just pull it up. Here you can see adding any of your primitives. Say you wanted to add a cylinder. I've added 2 cylinders. And then you have a sphere. And then we can create a new object from actually subtracting the 2 from each other, or create a union of them. And from this, you can create relatively complex geometries. However, we do also have full CAD import, of which any step file or STL file can be used. And as I previously mentioned, this healing process is one that's of particular importance. If a CAD file has errors when it was exported, we can take care of them automatically. We also have a robust materials database for this. By default, there's about 700 materials. And for an example here, say you can create an aluminum alloy if you were interested in a particular type of aluminum, not just standard aluminum, with the components of aluminum, silicon, magnesium, all created through our GUI. And if you do have a complex geometry, like that case I showed earlier where we had about 500 parts, we can actually use an external file to specify all of the materials all at once, rather than having to click through and do it individually, which could get pretty tedious for 500. Our particle sources, as I mentioned before, we have 4 types: spherical surfaces, as well as box surfaces, planar sources, point and volume sources. Of those source types, you can then specify a type of particle shoot, that being an electron, ion of any type, neutron, protons, or gammas. There's also an angular distribution that can be given to those particles. For example, often a planar source will use a beam source shooting the particles in one direction, or an omnidirectional source can make sure they're coming from all sides of the spherical source. The energy specification has multiple options available to it, such as monoenergetic power law, linear and exponential growth in the energy, as well as two types of external files that can be used, that being a two-column file and a weighted particle distribution. We'll get into the weighted particle distributions a little bit later, but something like a two-column file can basically give you the differential fluence of those particles and then their energy level. And the weighted particle can take the same data and manipulate it somewhat in order to improve your simulation statistics. And all of these results can be normalized to the source size, energy, and angle, and total number of particles for the simulation. The idea being that you can get your dose per particle effectively. We do also have many tallies available, as you can see here. Some of the most commons that we'll use is something like a fluence or an energy deposit, but you can also track the number of tracks or the population of particles in a single species. These can all be applied to, here we're showing a mesh tally and a volume. The volume is assigned to a shape or CAD file, and the mesh is an arbitrary mesh of your own creation. We do also, new for RSim 3.0, have the ability to specify probe tallies. A probe is a small piece of the simulation which you can place something and actually change the material of it, of whatever is inside that probe, without having to modify the simulation's parts. Now, this is really useful for things like if you wanted to stick a little water, probe full and fill it with water where normally there'd be air, to get a better estimation of what the dose would be for that area, which right now in your simulation would just be air. One of the best use cases we have for mesh tallies is to, in effect, create a heat map of a tally quantity. In this case here, you can see our energy deposition. We can see how the knee doesn't get nearly as much energy deposited in this simulation as the chest does. And so we'd obviously be thinking here, okay, we need to add some shielding to make sure to protect the chest. New in RSim 3.0 is also a concept called geometric biasing. Geometric biasing is a concept that allows for the significant reduction of error in complex shielding scenarios. Basically, what it does is, if you have it only will work with a spherical source. If you have a spherical particle source, you can pick an inner sphere and a number of spheres between that outermost sphere and innermost sphere. What will happen is, as a particle passes into a sphere, the number of particles is actually doubled, but their weight is cut in half. Similarly, if a particle is leaving the sphere, the number of particles may be cut in half with their weight being doubled. What this allows for, and particularly in complex shielding scenarios, is if you have a large shield that you know will capture and stop a large number of particles in the simulation, you can then, using this geometric biasing, boost the number of particles that are seen inside that layer of shielding while keeping your physics consistent because the weight of them has gone down. So you can get a better understanding of particle distribution inside that shielded layer while using far less particles and, as a result, simulation time than you normally would. Source biasing is one that I alluded to before. This is a concept that will take a two-column file of differential fluence and energies and actually reweight the particles based on particle energy. What this does is allows for a higher representation of higher energy particles in the simulation that you know will be penetrating further through a layer of shielding. So this will end up increasing the uncertainty and error if you are looking at the dose through only a thin layer of shielding, but as your thickness increases, you'll be decreasing that error. Looking at the distribution here. So this is a standard file that we use, and here's what a standard two-column file would have: the distribution of these are the number of particles on Y and the energy of them in X. When we use the weighted distribution, you can see that we have much more particles available at higher energies compared to the standard distribution. So we'll see the impacts of these particles more readily. So now we're going to go through a couple examples of RSim's capabilities. The first one here is a pretty standard case. Basically, what we're going to do is create a block of aluminum and shoot particles at it into this thing and look at the flux as we increase depth, seeing how far particles are penetrating into the aluminum. So here's our basic problem setup. You can see this is our standard window where we have our materials a lot set up. In this case, I used the aluminum for this block. This is our target box. You can't quite see it due to the shadowing, but there's a small planar source that will be shooting particles into this box that's not as big as the entire box is. And then we have our surface flux meshes being created. These surface flux meshes are very finely resolved along the length direction of the box, allowing us to create that heat map I had mentioned. One thing I had is they also allow us to filter so we can see the number of protons, alphas, electrons, and gamma particles. Here's a slide for that. So you can see here, with this high density mesh that we create and filtering, we'll know exactly the contributions of each particle type, how far each particle type gets into the simulation. So here, with a weighted distribution, we can see the flux of the electrons. And one curious thing we'll see is the number starts off reasonably high, it starts going down, and then actually increases right here. What ends up happening here is this is where the number of particles that are getting stopped as they start to run out of energy is greatest right about here. So we can tell our thickness is really only needs to be about this far in to get most particles. Now, if we were to run the same simulation, but using that weighted distribution I mentioned earlier, where we have a higher number of higher energy particles, we can see a significantly higher penetration of electrons and greater uniformity through, as we can see, these are some of those higher energy particles getting stopped here. You can also see these, some above and below. What these actually are is those higher energy particles getting deflected up and down as they're being shot in straight this way. Here we have the second part of second simulation setup. This is a example. If you were to download a trial of RSim 3 this afternoon, you can fire up directly, called the human in Orion. What we have here is a STL representation of the Orion module and a step file of a basic human model. There's leg, chest, arm, not as detailed as you could use in RSim, something that could be, for example, modeling individual organs, but this is one that we find convenient for setting up these basic types of problems, as it is easily used. For this example, we use a weighted energy distribution, with the goal being to study how the human is impacted over the dose on the Orion module. So this entire module is wrapped in a sphere and shot with a spectrum actually pulled from data on what you would submission to Europa. Here you can see the results for it. We actually have our human model here, and I've stripped away the units just for this presentation, but you can see the color coding on how the chest and head have the highest energy deposition. Since it looks like we do have some time, we can actually also take this simulation and rerun it with geometric biasing, which I will open up right now. And over here is our module. You can see the red sphere is our particle source. The geometry of our Orion module, we can actually take, if we wanted to look inside this thing, we can take it, take its color, reduce the opacity to say 50, and now we can see through it. There's a mesh tally there of a person. Here's our grid deposition of the entire person. We take that away and go in, then visualize our body assembly. Here's our body here. And all of this has, in this case, we're modeling the person as water, as people are about 70% water. We found that to be pretty effective. I happen to have already run this, but you can, I'll take a quick look at the run tab. And if I visualize it, we can see here, this is our person with, in this example here, I forgot to mention, is using our geometric biasing, where we have a spherical bias with 2 layers, our bias being centered around the same probe here. When we do this, we'll see that we get a little bit higher distribution of energy deposition, in this case on the legs. Or we can take a look. Actually, make this easier, I'll add a second view. Look at our energy deposit. And if we take a clip of it, you can see a small distribution there. We can also display our contours. Get rid of our clip. And so moving on, like all of TechX products, we do have, we understand that our complex problems require a complex solution. Many of our clients have simulation needs not previously solved by other applications, so customer support may be required for initial simulation setup during the evaluation period. In order to assist you in looking at the attendee list, I have assisted some of you in the past with RSim. We'll be able to help you set up any problems that you need. And as we're developing, particularly with RSim, a complex library of examples and tutorials and videos for some of these operations. In particular, things that we're looking at now are some of the CAD optimization things. So if you'd like to get some more information or request an evaluation, head over to txcorp.com. They'll have the entire documentation stack available for free. And if you set up, if you can also request an evaluation, we'll be able to get that set up with you. So now I'd like to open it up to any questions.
There are some features here. If you want to ask a question, you can, there's a Q&A box that you should be able to see, and you can type a question in there if anyone would like to ask anything. This has been really good, Peter. It's good to have an understanding on like the biasing and why that's such a neat addition to the product. So it looks like, and I just have a, oh, there we go. There's a question that came in through here. So question for that has been raised. What is the minimum thickness that can be treated by the code? The application I have in mind is low energy, and a low energy proton and electron dose in thin coatings and polymers used in thermal control materials on spacecraft. The range of polymer thickness is tens of microns to perhaps 250 microns with aluminum or other coatings of 500 angstroms to 1,000 angstroms.
So that is a good question. We'll probably definitely want to work with you a little bit in setting up that problem. However, there is no real thickness limit to the code. We just will need to make sure that your simulation is properly tuned down in all of its scaling of how much energy to be treating particles with. The example I could give you here, and this is one of our basic settings, is how to cut particles. The idea being that if a particle can't travel this given distance, it's removed from the simulation. For something like your application with these very thin thicknesses, we would actually want to make sure that we have all of those specified as angstroms. But after we've done that, I don't see there being a particular issue.
Okay. Good question. Another question, angular sources mentioned in the webinar include 1D beam, isotropic, and omnidirectional sources. Can a user specify an anisotropic beam?
Would it be possible for you to specify a little bit more on what you mean by anisotropic beam? One thing that we can do, I'll just open up a new simulation right here to show, is if we have our planar source and we do a 1D beam, you can have a dispersion angle given to that beam. It is also possible you can pick a point to focus all the particles to aim at.
It says, we've talked about how a monoenergetic beam is a source option. Can a user specify multiple beams?
Yes. So you can specify any number of particle sources for the simulation. You do have to make sure they're not overlapping each other, but otherwise there's no issue with that, doing that. And varying the flux with angular distribution, I see, is also coming through as a question. That I think we'd have to, I do believe it's possible. We'd probably have to work with you a little bit to make sure it's properly set up. In some ways, so the specification of that angular distribution can help get you there to have the flux varying.
So that's why you talked about how we support clients and help them at the beginning, right? If we need to, for any of these situations. What of these Geant4 physics packages does RSim use? Does it include the electromagnetic interactions, including secondary electron generation and transport?
Correct. Secondary electrons and the electromagnetic package we can see here is, if you happen to be familiar with Geant in the EM physics, they call them option 0, 1, 2, 3, 4 are the most common ones used, all of which can create secondary electrons.
Great questions. How about photo emission?
Photo emission, I have to think about photo emission is a it does not look like we currently include the photo emission model, but I will have to get back to you on that.
Okay. And if you want to go back to that final screen with the email addresses, that way, if anyone has follow-up questions, perfect. Great questions, though. Are the sources all charged particles, or can a photon source be specified X-rays or gamma rays?
Gamma rays can be specified. So I'll show you right here are particles available, or particle types. So electron, proton, neutron, positron, alpha, gamma, ions. And GNT is a computational construct often used to validate a simulation, but you can't use them for real physics. But we can do gammas. One thing we've talked about doing as well, and I can help you set up, is the actual creation of X-rays using electrons and tungsten. Is something I've done in the past.
Excellent. And as Peter said, and I'm going to plug again, is if anyone would like to get an evaluation copy of RSim, it is available for Mac OS, Windows, or Linux. And if you go to the TechX website on the upper right, it'll say request evaluation. And from there, you can submit a request for any of our software products, and you get an evaluation copy for 30 days so that you can try out the product, and we can work with you and make sure that it will work for your problem. And you may even get to talk to Peter again. Any final questions? That might be all we have for today. Thank you, Peter, for taking the time to put this on. We will be taking the recording from today, and we'll get it up on YouTube in a few days so that users can have access to it. For any other, if they want to look through it, see it again, and use it as they work through the product as well. And we do have some additional tutorials for all of our products on our YouTube channel as well. Okay. On that note, I think we can go ahead and wrap up for today. Thank you so very much, Peter.
Yep. Thanks everyone for coming out. Hope to work with some of you on evaluations in the near future here.
All right. Have a good day, everyone. Thank you.